Okay, so as Eugenio, I was also grad student here before, and because it's also a special place for me, so I prepared a special seminar that I haven't given before, so let's see how it goes. So I hopefully I will be short, and I will be speaking about something that you basically should know. It's old stuff. Basically everything was probably done before I was born, so it's not something which is almost. So it should be familiar. And let's see. Yeah. So there is the short outline. So I will give some motivation why I'm talking this stuff, and then go back to pre-QCD era and see that what we can actually say about the scattering amplitude without knowing anything about the QCD. And then I'm talking about gluon regularization. And this, I don't need the regularization, but I need a side product of that. I want to know that how the 2 to n scattering amplitudes in QCD can be written at the higher G limit. And this is, I will do the derivation to leading log accuracy. And so I say Recce, and there's a lot of Italians, so I asked from Eugenio, and Eugenio said that it depends on the region where you are, how to pronounce it, but I don't know. Is it the correct?
It's still Recce.
Right. No, I was thinking if we did in the northeast, maybe it was more like German speaking. But the Wikipedia says from Turin, so it should be Recce, right?
Okay,
Recce
so I'm fine.
Has anybody of you seen to the Recce? I mean, at a talk?
No.
Would you just... My first private lecture I heard was by Tullio Recce in Napoli. He was giving at the State University. Maybe I was finishing the high school. And he gave a lecture in Napoli, in San Carlo, which is the local opera theater. It was actually, it was actually on a wheelchair at one point. And he gave a general lecture about energy physics. This must be in the 90s, end of the 80s, early 90s, when I finished my high school. It's a really gentleman. The two gentlemen I've met in this field was really in this kind of movie, and it was fantastic and disgusting. It was also the beginning of string theory.
And then I will, if I have time, I will try to go through at least up to this point, and then if I have time, I will go through the how to, why these amplitudes are not very good by themselves to use it for LHC physics, but I need to do something more that I can have amplitudes that I can actually use. So, as a general motivation, this is one of the event displays from CMS. So, we collide protons and there is huge amount of stuff coming out, and there will be even more stuff coming out when they start the new run next year, or this year.
This year,
couple of months, and I'm still in the phase to change the year. So here is the theorist view of the same thing, and there's this part that we think that we know it, at least at some level. There is stuff that we have to fit, the non-measurable stuff that we don't have any control about. And then there is something underlying event, it's this kind of stuff that is some kind of non-measurable physics that some people might have some kind of idea that how to model it, but no one really knows what is the true nature of it. And I will be concentrating on the perturbative stuff and and what are the problems that can arise even when you use a perturbation theory. So I'm thinking about this kind of intermediate momentum region. that I'm perturbative, but still the momentum transfer, for example, due to the scattering, the momentum transfer is very small. So, for example, think about tight jet production, two jets that are far apart, and you have large invariant mass between the jets, but you have small momentum transfer. So then you can have, always when you have a hierarchy of scales, you have to worry about the logarithms of these scales, and because they can spoil the expansion of alpha s. So for example, if I have a large logarithm and then I have the alpha s, if I combine them, I have something of the order 1, and actually my perturbative expansion is going to break down. So I have to resum, in this case, these logarithms to all orders. And this is the reason that why I'm considering the high energy amplitudes. If you think about, for example, Barton shower, there you have the collinear splittings and you have the simple form for these splittings that you can resum. So I want the amplitude to be simple enough that I can actually do the resumation to all orders. And here, why I say that there is for example, this will cause that there is a lot of jets, for example. If you, how it arises is that if you have the jets far apart, then the energy that you take from the Barton distributions is basically determined by the jets that are most forward and most backward. And then if you do any emissions between, that doesn't cost you any phase space. So you can actually have multi-jet production at the LHC. So this is just another manifestation of these logarithms that will spoil the expansion. So if you go to the pre-QCD stuff, so S-matrix theory, so you impose 3 postulates that your S-matrix have to be, of course, Lorentz invariant, unitary, and analytic. And then all of these 3 postulates have some conditions that you can deduce. So, for example, Lorentz invariance is that I will be talking about 2-to-2 case most of the time. So we have the amplitude, and this will be a function of some Lorentz invariant products of the 4 momenta. So, for example, you can write in terms of Mandelstam variables. And for 2-to-2 case, you can express it in terms of S and T, and the U is dependent on the S and T, so U is the independent parameter. But sometimes I will write also the U here just because of the symmetries. And now there was one of the conditions for unitarity. So if the S matrix is just the overlap of the basically three states in the minus infinite and plus infinite sign. So I can write my S matrix in terms of what is called the T matrix and just the simple trivial scattering. And the consequence from the unitarity is that you can have this is what is called the Kapkowski rules, that you can actually write down the imaginary part in terms of all the sum of all intermediate stuff you can have here. And then analyticity, for example, you can one consequence is that you can write the imaginary part in this form. This just says that you have at some point you have the 2-particle threshold or whatever number of particles you want to produce, and then you have the discontinuity usually along the S axis, and then the imaginary part it's just the amplitude from the both sides of this cut. Other consequences, crossing symmetry, just that basically you can analytically continue the amplitude to a different region. So, for example, if you have the T channel, the U channel, then this you can express in terms of the S channel amplitude if you just swap the S and T, and the same for the T channel amplitude. If you swap the U and S, then you can express it in terms of S channel amplitude. And then, of course, if you use the Cauchy theorem, you can write down the dispersion relation, or if your amplitude is not vanishing fast enough, then you can write down the subtracted dispersion relation. So this is useful if you, for example, you can just find out what is the imaginary part of the amplitude, and then using the imaginary part you can reconstruct the whole amplitude. So this is useful if you do loop calculations usually. You use something like this. Okay, so let's think about 2-to-2 scattering in a T channel and write the partial phase expansion for this amplitude. So I can I can write the so this is in the limit that I can neglect all the masses. So I can write the cosine of the scattering angle to be as 1 plus 2 over T divided by S, and then so this is just Legendre polynomial. Yeah, and this is the partial wave amplitude, and then you have just the free factor, which is the angular moment. And now you can use the crossing symmetry to actually write it in the terms of S-channel amplitude. And then you can do something which is called Sommerfeld-Watson transform. That you can write the sum in terms of an integral. So you have a contour integral, and you can express the sum. And now, of course, what you have to worry here is that when you another point is that then you have to, we are here going to a complex plane, so that the angular moment can be have a complex variable, can be complex. So yeah, so this is just a generalization of the partial wave amplitude to a complex plane.
So just understand, before you have the ordinary Legendre PL 1 plus 2 ST, why in the contour integral is written P of L?
Because I'm allowing it to be on the complex plane.
Okay, so this is not the real Legendre polynomial.
No, then in this, when I call this contour integral representation, I'm going to allow that I can have complex angular moment. So this is the
complex.
Sorry?
L is complex.
L can be complex. And now you have to worry that you can do this continuation from the real to a complex, so that you have a unique representation.
Also, what you have done, you are basically changed the sum with an integral.
Yes.
Over a closed contour.
Yes. And this actually, there is a theorem by Carlson from early 1900s that is actually because that the partial wave amplitude changes sign. This is not actually unique, and you need to do a separate, basically this separately for plus and minus signs, and then you can show that it is actually unique representation of this stuff. And one step more, I actually forgot to, sorry, there is a figure missing. So I have the complex plane, and earlier I had the integration contour that goes along the over the axis in the integral, and I'm going to deform it to an integral which is vertical in the next line. And then these partial wave amplitudes can have poles on the complex plane that are called Recce poles. So these yeah. And now if I do the deformation, so I will deform my integration contour to be what I call C prime, then I put the residue from every Recce pole that I have. So these are just the complex poles of the scattering amplitude. And then I can write down the amplitude as so I have an integral along this line, and then I have to sum up the Recce poles, contribution from the Recce poles. And to be short, it turns out that actually the contribution from this contour integral along the vertical line is going to be 0, and I'm only left with the contribution from this Recce poles. And now I want to go to the very high energy limit or Recce limit, where S is much larger than T, and I can use the asymptotic behavior of these Legendre polynomials to write down the amplitude in the high energy limit in this form. So what I actually was after that here was that I wanted to figure out that what is the high energy behavior of the amplitude in the limit where S is much larger to T. And this I will need later on. And there's another thing that you can actually write down. You can shuffle the bits around, and you can write the amplitude so that it actually looks like that you have some kind of coupling, another coupling, and then you pick up a pole every time when basically
every time you hit it's zero in the gamma function.
yes.
Multiply it per time.
Yes. So this looks like I have some kind of T-channel exchange, and that would be called Recce. So you have some kind of generalized particle which has angular momenta. Of course, it's not angular momenta because it can have all the values.
You call it angular momentum because if
you go to the
certain particle with angular momentum, the contribution in the channel from the particle is directly proportional to the spin.
Yes.
But the S to the alpha you get is to the fact that if you were to couple, and that would be a real particle, you would have enough derivatives to compensate for the angular momentum, so that would be actually S to the particular kinetics in that part.
Yes. But what I really now need is just that I need the form of the amplitude at the high energy limit. Okay, so the another thing that I have, so I want to show is something that is a gluon Recceization. So if saying that something Recceizes is to say that the amplitude behaves like this in the high energy limit. So if I can show that the gluon behaves like this in the high energy limit, then I would say that the gluon Recceizes.
But I mean, this is the contribution from one single piece. because the entire amplitude must be finite. It must be still unitary, as we say.
Mm.
So that so in other words, in QCD, the largest behavior of that must be at most logarithmic.
Mm.
So it means that you have an infinite number of these states that conspire to a log function. Each of them can be seemingly be divergent in S, but the full sum must be at most logarithmically divergent, as you produce the log dependence of any amplitude in QCD, because QCD is finite.
Mm.
It must be in this truly asymptotic regime of QCD, all the amplitudes must go at most logarithmically divergent. The cross sections have to be finite. But that is the contribution from one redshift.
Yes.
So each of them can be seemingly
Then you can.
grow with S,
Yes.
but the full amplitude cannot.
Yeah.
Explain to the people.
And okay, so what I basically, to show this behavior, I want to calculate the 2-to-2 scattering to any order in perturbation theory. And of course, I cannot do the full calculation to any order in the perturbation theory, so I'm only going to take the leading log in S over T into account and say that this is my leading contribution, and then I can actually do the calculation. This can be shown to work also next to leading log. I will do only for the leading log. So I have 2-to-2 scattering, and then I have a gluon exchange at the leading order, and the momentum transfer is I denote with Q. So I can write the Q in Sudoku representation, so in terms of what is the portion of energy that I take from the P1 and P2. And then, okay, just as kinematics, I'm going to be on the center of mass frame. And if I use the on-shellness of the particles, I say that all the particles are on-shell, all the coming particles are on-shell, I can actually show that the T is actually just proportional to the transfer scale in the problem. And now I'm in the Retscher limit, so if the momentum exchange in the amplitude is small, it's basically, I have here a major, and so this angle bracket is just the U spinner with some helicity. So this is just notation. So I could write this with the U, with the U's as well. And now, because normally you would have P1 plus Q, but the Q is so small that I can actually approximate it to PP1. So this will give me 2 times the P1 mu, and here I would get 2 times the P2 mu. And then if I just calculate what is the P1 dot P2, that will be something like S over 2. And then I get this one times the color factor here. So all the calculations will be simple. You can do them back of the envelope at any time. So then if I want to go to the next order, then I have 2 cases that I have to consider. And now I can use the Katkowski rules. So I will just cut here, put the internal lines on shell, and do the 2-body phase-space integration and calculate the imaginary part. And this, if I do the same thing that I got, and then this will be basically related this with the crossing symmetry. So if I calculate the imaginary part or the real part of whatever here, I will get another one if I just replace S with the U. And another thing to remember is that if I go to the high energy limit, the U is minus S.
Oh, sorry, but in the case of QCD that you had was, these are assumed as 2
yes.
gluons.
Yeah. So then I have the vertex corrections, I have the shell energy corrections. But this.
Sorry,
No?
but you have also interactions, which is the 4 gluons, so there's something in the middle. I mean, the four gluons mixing in the center. I assume these ones are not mixing, are not interacting.
No, but that would be higher order.
Higher order.
That would be higher order. So this is just the first order out.
Just higher order.
So I want to calculate the all orders. So this is just to show that if I use the Katkowski rule, then I have the 3-level 2 to 2 amplitudes and then the complex conjugate of that. I can write the phase-space integration in terms of these pseudo parameters and get this kind of result. I will keep this term here, and then I can basically, this here is the first order result times alpha 2 pi. And then I have the imaginary part. I can just figure out that if I know that the S over T is negative, I can just figure out what is the real part. It's a simple calculation. And then I get the real part. And now, as I said before, I can just replace use the crossing symmetry, replace the U with the S, and use the Rechel limit. Of course, now I have to be careful. If I have the cross diagram, I have the different color factor. So I need to also take care of that. So then if I combine that with this real part, I can basically have the leading log contribution now to first order, or first non-trivial order. And basically I can do the same thing here. So now if I do the next order, okay, here is a line missing. So I have basically 2 to 3 amplitude that I cut, or 2 amplitude that I cut, so I always have 2 to 3 amplitudes in the calculation. Or then there is another set of diagrams like this, and then this reversed. So basically I have 2 different kind of contributions that I have to calculate. And I can again I can do this without decomposition. And okay, here basically I can show that these cannot be equal, or there is ordering because the cutted lines have to have a positive energy always, and that there is a strong ordering comes if you do the integral. You can show that it's only fixed the contribution from the region that you have strong ordering between these pseudo variables. And there's just some kinetics. And if I think about 2 to 3 amplitudes only, I can basically I have here the contribution that I'm radiating the gluon from the other gluon, so I have the 3 gluon vertex. And here, if I radiate the gluon from the upper fermion line or the lower fermion line somewhere. So I can combine all these contributions and write down this 2 to 3 amplitude with an effective vertex. So I basically have, I can take care of the gluon radiation in this limit, writing just an effective vertex. It will be a non-local because I have this depends also on the momenta of these lines. And now I can do the same thing as before. I can use the Katkowski rules to calculate the imaginary part. And this is okay. I don't know why. Yeah, I should have already done this integral. I wrote the wrong relation. In any case, when you basically do this integral, you will get the log of S over the transit momentum. And then you have the other set of diagrams which would proceed in the same way, that you just calculate with the Katkowski rule, calculate the amplitudes. And then you combine. And then you got the real part that looks something like this. So now I have calculated the basically first leading orders. So this starts to look like something like an expansion of S over K to the epsilon, where this was the transverse momentum integral. So this has something similar than what I said from the S matrix theory, that how the amplitude should behave. So now if I want to do it to any order, if I want, so I have to basically write down 2 to n scattering amplitude. And so basically in this limit, if we are in the Rachel limit, it doesn't matter that do we have basically a gluon radiating off from the fermion line or gluon radiating off from the gluon line, because you have the same factor, only the color coefficient changes. So in the end, always you can write down 2 to n amplitudes in terms of these effective vertices, and basically you have an effective vertex and complicated color factor. And this you can prove if you use gauge invariance or something. The proof is not very complicated, and I had in the first lines a couple of books as a reference, and the proof is explained in both of these books. But heuristically, the idea is that you can always combine these gluons to an effective vertices, so you have just a ladder of effective vertices, basically. Okay, so now remember that we have these two kind of, I had this, okay, I will go back. Two different kinds of amplitudes. So now I know that how to do this in 2 to n case. But then I would have also this, if I to have the complete imaginary part, I should also calculate what is the counterpart of these in the 2 to n case. So I would have basically a ladder, and then I would have an expansion of all these sub-ladders in a different way. So that would be extremely complicated amplitude calculation. So because of this, that if you calculate a couple of first orders, it looks like an expansion of S to the power of this epsilon. So you can do an ansatz, it's called the Lipotov ansatz, that the regularization is actually equal to replacing all the gluon propagators in the ladder, in the vertical lines, with this kind of propagator. That you have the normal Feynman gauge propagator, and then you have this extra part, which should capture all the virtual corrections. And now I know from the S matrix theory that what is the behavior of this amplitude in the high energy limit. So now to show that this works, I have to show that this is consistent, that if I use this ansatz, I actually get the proper behavior in the high energy limit. So now I can write this 2 to n amplitude. So this is the same formula as before, but I have just replaced all these propagators with this according to this ansatz. So then this part is a bit more lengthy, so I just outlined what are the steps, and you can do the calculation if you wish. But so to calculate the imaginary part, then now you have to sum over all the amplitudes from 0 to infinity. So how many extra gluons you radiate off. So you can do the Sudakov parameterization for each of these gluons, and then you would have a nested integrals basically over the Sudakov parameters. and that would be complicated to do, but what you usually do when you have nested integrals, you go to Mellin space, use the convolution formula, and then you get some kind of integral equation between these integrals. So this turns out that this integral equation is actually has a very simple answer, which you can when you solve it, and after this lengthy steps, you actually find out that when you also add the cross channel, that you exactly get the form that you want. So this says that the ansatz was consistent. Okay, so it says that this is proper 2 to n amplitude to leading log accuracy. And now, okay, probably go through this quite quickly. Okay, so now if I go back to the leading order amplitude, so if I just consider 2 to n amplitude at tree level, so this is the earlier amplitude without this modified propagator, I square the amplitude, and then this amplitude simplify in this kind of very simple form. So again, I have basically some kind of vertex factor or impact factor. I have an effective vertex. So if I take the square of that effective vertex that I had earlier, at the limit I end up with this kind of very simple things. This is called the Lipatov effective vertex. And as I say that in this Eikenal limit, basically it doesn't matter if I radiate the gluon from the fermion gluon line. These amplitudes have the same form if I have gluon to n gluons, or 2 quarks to 2 quarks and n minus 2 gluons, or gluon and quark to n minus 1 gluons. Only the color factor changes.
Is it easy to understand intuitively why should be the case that it doesn't matter if it's related by the gluon? Maybe I missed this.
So this is the normal tree gluon vertex. So now, if I am in the Heinrich limit, I can just basically neglect the Q, and call the momenta, and I'm left with this factor. And this is the normal fermion gluon vertex. So it's just this simple thing that you take the limit and B is much larger than the Q. Okay, so if you look at these amplitudes, these only depend on the transverse moment, not on the rapidity of the particles.
So this capital Q is not small q as soon as squared. So this capital Q in the last.
That it basically this other quark can be the same quark, it can be the anti-quark, it can be any quark.
Oh, it's just a spectrum.
Yeah.
So it's just scattering up.
So it's just two scattering. Basically two quarks goes in, 2 quarks comes out, and then you have some number of gluons. And then you have strong ordering. So I had earlier the ordering in the Sudakov parameters, but if you just play with the kinematics, the ordering in the Sudakov parameters translates to ordering in the rapidities of the particles. But of course, because this amplitude doesn't depend on the rapidity, if you plot the amplitude as a function of the maximum rapidity difference that you can have, then in the limit that would be just straight line. And of course, if you this is the full amplitude taken basically from MapGraph. You can calculate by hand. Not very complicated. So it has this kind of behavior. So of course, here in the region that matters, you are way off. So if you want to do some kind of pheno with these amplitudes, high energy amplitudes, you are guaranteed that you will do very badly. And it's even worse, because if you have quark Hall scattering, or even quark glue scattering, then these amplitudes only have the t-channel pole. So these factorize by default. You don't have to do anything with these factors, and still you don't even capture these scatterings. So I'm working with the Monte Carlo code that is called high energy jets, and basically these are the requirements or the improvements that you want to do when you want to modify these amplitudes and have actually something that you can use. So you want to keep the t-channel factorization, because then you have simple form and you can actually do the resumation to any order. So what I talked about before, these are actually not gauge invariant. These are gauge invariant only in the limit. So I want something which is really gauge invariant in point by point in phase space. And then I want to also, at least I want to capture the amplitudes that factorized by default without tuning. And then, okay, I want to be exclusive, so I want to have access to all the formula. And why I want to keep the t-channel factorization? Except that it simplifies things. But also here, this is just the 2-2 scattering, and these contributions actually dominate, which are ordered according to this ordering that dominates in the high energy limit. These contributions are the dominant ones, also away from the high energy limit. So if I capture these amplitudes, then I capture the most of the cross section. So if I have a very good approximation for them, then I'm already doing pretty well. And then I can start to worry about this stuff that I cannot actually design.
Sorry, can you explain what's the FKI?
So this is the contributions. For example, if I have quark, and gluon, this would be FKL, because I have this amplitude survives to the high energy limit. But for example, if I have this kind of amplitude, this would be suppressed at the high energy limit. This behavior with this, because I need to have something. I can have 2 quarks and then some gluons, or gluon scattering. But if I have quarks coming in and gluons coming out, then this will be suppressed. And this is coming basically from the red jet theory. So I'm dominated by the exchange of the maximum with the particle of maximum spin. So all the contributions that I cannot have gluon exchange are suppressed at the high energy limit. So this is basically what red jet theory says.
So sorry, that process, the one on the top, is tried at a higher order. Right?
This is just that something happens here.
But the other two is this dominance.
Yeah. Yes. Because this is of the form that I can have basically quark current, and then I have an effective vertex. So this kind of contributions dominate. So now, okay, I can do the modifications I just showed. So instead of this amplitude that I have just written in terms of transverse momenta, I try to keep as much as possible. So now I postulate that the new amplitudes that I'm going to use are basically I have a construction of I have 2 to 2 amplitudes, and then I have a set of effective vertices that I will contract between. So the form is exactly the same basically that I had before. But now I'm not taking the exact limit if I don't need to. So for example, when I'm deriving the effective vertex, this goes in the same way, but I'm keeping all the terms except those that I really need to get rid of, that I can form this effective vertex. So I will keep more information than if I go to the exact limit, and I can show that this form of the vertex is actually gauge invariance. So if I dot it with the moment, and now I can actually get something which is pretty close to what it should be.
So you're keeping just some diagrams and then taking this direction, and you get the gauge invariance in this bit.
Basically what I'm doing is that when I derive my effective vertex, I'm not dropping out terms that I don't really need to, because there is so I'm only requiring them to be separated, but I don't require that all the momenta really goes to the high energy limit.
But how do you choose the terms that you don't want to drop?
Maybe let's revert the question. Assume we did not have markup. Assume I did not know the result. What is how would I choose it? Is there an organization principle?
Yes. So you write. You have basically you can here have the gluon coming from all these places, and I have so I'm only saying that these are ordered, and then terms that are subdominant in this order I'm throwing away. But I'm not writing all the momenta or all the terms in I'm not going to the strict high energy limit.
The question, yeah. So I guess, but if this is not, that means also not even getting high.
It turns out that it actually is.
Why? It's not easy to understand this.
I mean, is it a theorem, or if I go to the next leading order, just be nice.
No, this is just the first order in the loss. So in this you can just contract with the moment and show that it's a gauge invariant. So it's just a modification. You basically keep the information about the momenta, because if you go to the high energy limit, then you are only it's only the transverse momenta that matters. But now if I don't go to the high energy limit, then I keep the full form momentum information.
But again, this begs the question: how do I know what is the correct order?
Because
again, if I did not know the result.
But then you just check that you have the result, and then if you take the full limit, you get the correct one. Because you need to get, if you then go to the exact limit, then you need to get the correct one.
Maybe another way is saying, what is the control parameter between the blue line and the red line? What I'm actually using as a control parameter. But I mean, so you said it correctly that the straight line at 1.4, that is the correct, if you want, regular.
Mm-hmm.
And that has to be 1.
Yeah.
If you consider 1 over S corrections, that for some leading correction, S's are getting deformations from this straight line. Assume you were able to do it, this actually going from the complete high energy limit, and then reconstruct everything by adding one of the subleading corrections in S over T.
Mm-hmm.
So you made a parameter. So in the regular limit you have an S over T, which is much, much less than 1. And of course, if you go in that limit, you get a straight line. I think that's a bigger problem. But I also know that I will have S of T. So I'm trying to say whether there is
I basically, I think I was just expressing it. You don't do anything magic. you just
This
You-
is much.
yeah, but you just keep the form momentum as it is, and then
Can you put back the expression for the
Yep.
vertex?
So here you're technically not doing an expansion in SOT.
No. no, this is just an F.
So you keep a subset of diagrams with certain ordering.
Or
And this seems to capture most of the.
okay, I made fool of myself in a sense. I'm decoupling the terms that would decouple if I go to the SOT limit. So I'm in a sense doing the SOT thing. But from the rest of the terms,
You don't.
I don't drop more stuff anymore. And
So-
then I just have to make sure that the result is gauge invariant. Then what is left, I symmetrize in P1 or in the outgoing
So you
moment.
get crossing. You have crossing.
And then
You have crossing. You have getting minus capacity. Don't break it by hand. But you're throwing away objects which so that in the large S over T, in the small S over T, they would not be there.
mm,
In some other parts, there are also other parts of the computation that will also drop in the S over T range, which you actually keep.
mm,
And that is the magic.
yes, sure.
So there is a magic in that. So I mean, the magic is in the fact that in the terms, which in the part of the amplitudes that contain the S over T limit,
Mm,
you retain the subleading S over T.
yes.
Then there is another part which does not, that disappears in the S
Sure,
over T.
because
Those you
I'm-
don't consider anything, but they will also have a sub S over T
Yeah.
subleading.
But I'm saying that I want to be right only to leading log. So basically, it doesn't fix anything from the
But to
subleading
reproduce-
behavior.
But to reproduce the curve, we also need the subleading curve.
Yes, and this is basically I say that I want to be. I want something which is
But that can be just the reproduction of the curve from this argument, it can be just shear luck. On the mathematical point of view.
sure. Then you have to test it. That
No, so
Yeah,
it's, but it's interesting, so you're making an observation. If I take the terms that survive, the part of the amplitude that survive in the limit of S over T, and I retain also the subleading terms, they seem to capture well the madcap expression. That actually, at the end, is the heuristic thing.
it's just a leading one. Yeah.
If I it's a question of whether or not is it theorem or is it result, because it might still be a theorem, I don't know it, but it's not.
No. You just say that you want to conserve the momentum, and that the vertex is gauge invariant.
Maybe yeah, it's also clear to you now.
Yeah.
Yeah, I guess it's a gauge invariant, the requirement of the
Gauge,
invariant.
yes, yes.
So at least, yeah, certainly
Yeah.
these are the ones you can keep together,
Yeah.
because for any SOT.
So you can add any terms here that respect the gauge invariance and the form momentum conservation. Then if they are subleading, you don't have any control on them. So you just want it to be consistent. You just want to be form momentum conserve the form momentum and conserve to have the exact gauge invariance.
That's fine.
Yeah.
No, this is clear.
Yeah. Okay, I think I used all the time and a bit more. And then, okay, I will just conclude with one of the plots. So then you can build, for example, Monte Carlo, and based on that, and then you can check that how it works. And it seems to work very well. But in any case, if you have any questions or want to discuss, I'm happy to discuss. This was just that if you are interested about anything, then please come and ask.
Sorry, can I ask you?
Sure.
So I'm trying to understand what's the gain here. So if I mean, since I already math graph, this is really also the question I asked to Durham before. I mean, what is the gain, right?
The gain is that
what do I mean, does it make it easier to
the gain is that the expansion. So if you calculate with math graph, you can do order by order in alphas. And if you have high multiplicity jet production, where the jets are actually span a large rapidity span, then your alpha S expansion breaks down. So you do math graph leading on the calculation, you do next to leading on the calculation, you do next to leading on the calculation, but you cannot actually trust them because the next order will be always be the same. So this is one way to actually have the resumation and then to restore the dependence on the rapidity. Because if you do the exact limit thing, then you don't have the rapidity different dependence only on the log parts that are in the higher order in the logs. So, and this is something that they have done for many years. This is called PFKL, basically. And that's basically the problem of the PFKL, that you have the straight line in the leading of the matrix limit. And that will say that the PFKL will always fail, basically. So this is basically to say that you take the PFKL and then you try to reduce the assumptions that are behind and to get something. Because this will be crucial if they are doing, for example, this in the next run, any SUSI searches. Because there you almost always end up in the situation that you have many jets. And then you have to know that you can actually trust the tools that you used to calculate the background. Because you can do a model independent stuff if you are hunting a resonance. But if you are not trying to find the resonance, then you are bound to be model dependent. So you are very dependent how you model your standard model background. And that will be maybe a problem.